Okay, so you might recall that we were able to develop a power series for sine of x here. And so therefore, by replacing x with x squared, everywhere there's an x, replace it with x squared, we get a power series for the sine of x squared. Okay, so now if we wanted to integrate this function, which is a non-elementary function, from 0 to 1, well, since we don't have a formula to integrate sine of x squared, we could integrate its power series form, and then when we integrate its power series form, we just apply the power rule to each term, and then we would get here x cubed over 3, and this would be x to the 7th over 7 times 3 factorial, and this would be x to the 11th over 11 times 5 factorial, and so forth. And then if we integrate this from 0 to 1, we actually get 1/3 minus 1/42 plus 1 over 1320 minus 1 over 75,600, which is 0.3103. Now, the third term above is actually 1 over 1320, which is approximately 0.00076. So, since the third term has 3 zeros here, then that tells us that we could just take the first two terms, and those would be accurate within 0.001 of an error. So if you just take the first two terms, you get 0.310. Now, the fourth term above, 1 over 75,600, is accurate to 0.000013. So there's 4 zeros here. So that means that if we take the first three terms, that would have an error accurate to less than 0.0001. And so if I take those three terms, I get this. Now, if we were to take all four terms, we would get this, which is a very, very accurate value. Okay, and I probably should have given you the actual answer, but I tell you what you can do. You can go to Wolfram Alpha and ask it to integrate this for you on the interval from 0 to 1, and it'll give you the value for the answer. Okay, and it does it numerically because, like I said, there's no formula for that. Okay, let's talk about arctan. Earlier we derived a series for the arctan of x using the, well, actually shouldn't take that out, by integrating the series 1 over 1 plus x squared. And so remember, 1 over 1 plus x squared, we developed, this is the series for 1 over 1 plus x squared. So if we integrate that 1 over 1 plus x squared, that's actually going to give us arctan, because we know that if we integrate this from the formulas, we should get arctan. And so integrating this, since this series 1 over 1 plus x squared is equal to this, I mean the function 1 over 1 plus x squared equals this series, then if we integrate this series, we'll get x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, where the nth term is minus x to the n plus 1 over n plus 1. So, and we know that that should equal the arctan of x. So now I wonder how close we can get to solving arctan of 1. Okay, now we actually know the answer. We know that the solution to arctan of 1 is pi over 4, which is approximately 0.785398163397. I got that off of Wolfram Alpha. Okay, now if we use the first four terms from up here, 1 minus a third, we get 1 minus a third plus a fifth minus a seventh, and that gives me a value but it's not real, it's not very accurate, because 0.785 and 0.724, what that would round to 3 decimals, is fairly off by a distance. So we're not close. So let's try it with more terms. So I'm going to take it out to 1, 2, 3, 4, 5, 6, 7, 8 terms. And even with 8 terms, I'm a little closer, but I'm still quite a ways off between 7.8 and 7.5. So it appears I would have to take this out to a very large number of terms to get close to the actual result. Now the reason is because this series is centered near 0, but not at power 4. So actually these series approximations are much more accurate if the number is near 0, and of course power 4 is not near 0. So therefore, I'm sorry, I probably said that wrong. It's actually not the power 4 that's not near 0, it's the 1 that's not near 0. Okay? So at 1 it converges very slowly. Okay? Because 1 is I mean, I know it's relative, but for this case we need something closer to 0 to make this converge faster. And in the next example I can show you how we're going to outsmart this particular problem to try to get a solution that will converge to the answer quicker. Okay, so this is a clever technique. Here we're going to let A equal the arctan of 1/2, and B is going to be the arctan of 1/3. And so now you know that if you solve this for tan A would be 1/2, and this would be the same as saying tan of B would be 1/3. Now, there's an identity that says the tangent of A plus B is equal to tangent of A plus tangent of B over 1 minus tangent A times tangent B. Now, let me show you what I've got here. What happens? Since we know tangent of A is 1/2 and tangent of B is 1/3, then the numerator would be 1/2 plus 1/3. And in the denominator, we'd have 1 minus tangent A tangent B, so it'd be 1 minus 1/2 times 1/3. So that'd be 1 minus 1/6, which is 5/6. So this expression, if I evaluate it at tangent A and tangent B, would actually be 5/6 over 5/6, which is 1. And 1 is actually the tangent of power 4. Okay, so now we know that the tangent of A plus B is actually equal to the tangent of power 4. Therefore, power 4 must equal A plus B, and since A is the arctan of 1/2 and B is the arctan of 1/3, then we can represent power 4 as the arctan of 1/2 plus the arctan of 1/3. Now, since 1/2 and 1/3 are closer to 0 than the 1 that I used in the previous example, this arctan will converge much quicker. And so here, if you use the arctan series here, and remember I'm using the series for arctan of x, and so you can go back and look at that series, but it would be x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so forth. So if I plug 1/2 in for x, then I get 1/2 minus 1/2 cubed over 3 plus 1/2 to the 5th over 5 minus 1/2 to the 7th over 7. Now I just calculated those 4 terms and got 0.46346726195, and then I did the same thing for the argument for x equal 1/3, and when I evaluated the first 4 terms for that, I got 0.3217, and so on and so on. And then we know that since pi over 4 is supposed to be the sum of those two, then we can add those up, and we get the 0.785. We get actually 0.7852 with a bunch of other decimals, And if you remember earlier, I said pi over 4 is actually equal to 0.7854. So we're actually accurate to, well, I said 4 decimals, but it looks like maybe we're more accurate to 3 decimals. But anyway, we're much more accurate than we were earlier when we were trying to find, when we were trying to solve this answer, which was actually going to give me pi over 4 for the answer. Okay, so the point here is that up there we could have used that series to try to find out a value for pi over 4, but it didn't give us the answer quickly enough. But we outsmarted the series here, and we're able to get a value for pi over 4 by using this little trick of letting A and B represent these two arctans of numbers that are closer to 0. Okay, so we can evaluate this limit at 1. You'll get 0 over 0, so that's the indeterminate form. But what we could do here to evaluate this limit is we could actually write the natural log of x as a Taylor series using powers of x minus 1. So therefore it'd be centered at x equal 1. So you could write the natural log of x as x minus 1 minus a half times x minus 1 squared plus a 6 times x minus 1 cubed, and so forth. So just look up the power series representation for natural log of x. I don't know if I've covered that one exactly, but go ahead and look it up and you'll see that this is the power series for natural log of x when it's centered at x equal 1. Now, going back to this limit, we have the natural log of x, which we're representing by this power series, and then we're going to divide that by x minus 1. Well, what's going to happen is if you divide the first term by x minus 1, you're going to get 1. But if you divide all the other terms by x minus 1, you're actually going to have a factor of x minus 1 in all the other terms. So when you take the limit of this as x goes to 1, then all these other terms become 0, and all you end up with the 1. So therefore, the limit would be 1 minus 0 plus 0, and so on, which is just going to be 1. Now this next limit, I did something different here. The limit of sine x minus tangent x over x cubed. This also becomes 0 over 0, which is indeterminate. Well, sine x you can write as this, and tangent x you can write as this power series. And so I'm going to go ahead and see what happens if I evaluate sine x minus tangent x over x cubed. So if I do that, here's the sine x power series over x cubed, and then here's the tangent x power series over x cubed. And then if I put those together, I basically get these terms minus these terms, so it just changes their signs. Now notice that the x's will cancel, and so you will have these terms over x cubed. Okay, and so now what I can do there is I can actually factor out an x squared, an x cubed. I can factor out an x cubed, and when I factor out an x cubed, I get minus 1/6 plus x squared over 5 factorial, and then minus a third minus 2x squared over factorial. That should be a cubed as well. Alright, so I have x cubed here over x cubed, and then notice here if you do minus a 6 minus a third, that's actually going to equal minus a half, and then all of the other terms have x's in them. So if you take the limit, of this expression as x goes to 0, all of these terms will disappear. So all the other terms will disappear, and you'll just get minus a half. So that limit is actually equal to negative a half. Now I'm just going to leave you with a list of the series that we've talked about thus far, and in the next video I'll introduce the Fourier series, but I'm going to slowly scroll through so you can see the series that we've developed in this chapter. We may not have developed all of them, but these are the series that we have. We have some series for rational functions, series for e to the x, series for sine x, cosine x, natural logs, and then we end with the binomial series. So that's the end of this video.